Hi, do you want to know why galaxies orbit faster than we would predict? Do you want to know what dark matter is? Did you know we can calculate the orbital velocity at any point in a galaxy using visible mass? Or calculate the visible mass using the orbital velocity? If you want to know the answer to these questions and much, much more, then you've come to the right place. Ladies and gentlemen, boys and girls, hello and welcome. My name is Mark Hatfull, and today we're going to be talking about gravity. We're going to try and make gravity as simple and easy to understand as possible, and we're going to look at a different way of contemplating gravity and thinking about it. We're going to think about how gravity could work for galaxies, and then we're going to come up with a formula to calculate the gravity around galaxies. So when we think of gravity, we think of space-time and we think of mass curving space-time, and that curved space-time results in the effect of gravity. But is there a simpler way to think about it? Let's go back to basics. If we want to know the force of gravity, then we only need to know two things. We need to know the mass, and we need to know the area around that mass. If we increase the mass, then we increase the force of gravity. If we decrease the mass, we decrease the force of gravity. If we increase the area around the mass, we decrease the force of gravity. And if we decrease the area around the mass, we increase the force of gravity. So we can effectively say gravity equals mass divided by area. And that's exactly what Newton did when he came up with his formula for gravity. So he says that gravity is equal to the gravitational constant times the mass, which is equivalent to the mass, divided by the radius squared, which is effectively the area. But the radius squared isn't exactly the surface area of a sphere. In fact, if we wanted to use the surface area of a sphere, we'd need to use 4 pi radius squared. So if we go back to Newton's formula, we can adapt his formula so we're specifically looking at the area of a sphere. We can do this by adding 4 pi r squared instead of r squared. And to do this, we need to add 4 pi to the gravitational constant as well. So if we have 4 pi and the gravitational constant, then these are all constants, and we can shorten that down to a new constant, which I've labeled Vx. So now if we want to know the force of gravity, we can take the mass and divide it by the surface area of a sphere. And that gives us the formula gravity equals Vxm divided by 4 pi radius squared. But what about if we're trying to calculate the gravity around a galaxy? Well, when we use our formula for the surface area of a sphere on a galaxy, it doesn't work. In fact, no formula calculates the force of gravity around a galaxy, but that's because the galaxy is not a sphere. So if we're trying to calculate the surface area of a sphere around a galaxy, it doesn't work. When we try and calculate the force of gravity around a galaxy, we would expect that the force of gravity decreases the further away from that galaxy. But we don't see that. When we observe a galaxy, we see the force of gravity is much greater. If we know the force of gravity is equal to the mass divided by the surface area, and we're using the surface area of a sphere, when the galaxy is actually not in the shape of a sphere, then why don't we use the surface area for the shape of the galaxy? Why don't we use the surface area of a disk instead? So we can take gravity equals the mass divided by the surface area and replace the surface area of a sphere, 4 pi radius squared, with the new formula, the surface area of a disk, 2 pi rh. This gives us a new formula. Gravity equals Vxm, the mass, divided by the surface area of a disk, 2 pi rh. But what is the height? Well, this is just a short video, so I won't go into it here, but just so we know, the height is equal to the square root of 2 times the mass. So now we have a new formula. Gravity equals the mass, Vxm, divided by the surface area, which we're using the surface area of a disk. So 2 pi radius times the height, or 2 pi radius square root 2 times the mass. So let's take our new formula and match it against the data and see what happens. So this is galaxy N2403. This graph shows the force of gravity over the radius in meters for this galaxy. The blue line shows the calculated force of gravity with our formula above. The red line shows the force of gravity that we observe when we look at this galaxy. And as you can see, those lines match up pretty well. But what about other galaxies? Well, here's N1003. That works pretty well. Here's another galaxy, and another, and another, and another, and another, and another, and another, and another. And here's 4 more. You can see that they all match up pretty well. Here's another 4 as well. But that's not all. When we look at a galaxy, we see the visible mass and we see the orbital velocity. So we can calculate the orbital velocity from the visible mass. Well, the orbital velocity is when the centripetal acceleration equals the gravitational acceleration. We know the formula for the centripetal acceleration, and now we know the formula for the gravitational acceleration. So we can take those formulas and put them together to create a formula to calculate the orbital velocity from the visible mass alone, or a formula to calculate the visible mass from the orbital velocity. Here's galaxy DD0154, and as you can see, we've got the orbital velocity on versus the radius in meters, and our blue line is the calculated orbital velocity using the formula above, and the red line is the observed orbital velocity. And we can compare it to other galaxies as well, like M33 and N1560. And if we turn that formula around, we can take the orbital velocity and calculate the visible mass, just like in these examples here, or these ones here. So as you can see, the primary evidence for dark matter is the gravitational rotation curves. And if we can calculate the gravitational rotation curves using visible matter alone, we have no need to add an additional dark matter. So now we're left with the formula gravity equals mass divided by area. If we're looking for the gravity of a single object, then we can use the surface area of a sphere. If we're looking for the gravity around a galaxy, then we can use the surface area of a disk. And so now we can get the formulas for a single object as gravity equals the mass, Vxm, divided by the surface area of a sphere, 4 pi r squared. Or if we're looking at a galaxy, we can take the gravity as equal to the mass divided by the surface area of a disk, 2 pi rh, or 2 pi r square root 2m. So now, when we look at the galaxy rotation curves, we can take the visible matter and calculate the orbital velocity, and that is very similar to the observed orbital velocity. Therefore, we don't need to account for dark matter when calculating the orbital velocity of gravity of galaxies. So gravitational rotation curves are one of the primary evidence for dark matter, but it's not the only evidence for dark matter. There's also gravitational lensing, galaxy clusters and collisions, and cosmic microwave background radiation. So if you're interested to hear more about these, or if you're just interested in hearing about dark matter, dark energy, why the universe is flat, how the speed of light is constant, or is the universe infinite, you can watch more of my other videos. You can download my book for free in the link below, or if you're feeling generous, you can buy a hard copy on Amazon. But most importantly, if you can share this video, that would be greatly appreciated. If you can share this with friends and family that are interested, they may be able to share it with people that go to university. Those people may be able to share it with people that do physics. Those people may be able to share it with the physics faculty and physicists, and hopefully we can get some traction on these ideas. Thanks for listening. Have a good day.